We're going to talk about low-pass filter circuits, high-pass filter circuits, band-pass and band-stop filter circuits. Starting with low-pass filter circuits, a low-pass filter circuit passes signals with a frequency lower than a certain cutoff frequency and attenuates signals with the frequencies higher than the cutoff frequency. Cutoff frequency, also known as FC, will be equal to 1 over 2 pi RC. As you can see, we have a RLC circuit right here, set up as a low-pass filter. We also have RC circuit here as an example, as a low-pass filter. It is shown in the graph of the amplitude versus frequency. We will have the cutoff frequency right here, and this will be the signal. As you can see, the amplitude gets lower because it attenuates the signals that passes through the cutoff frequency. Anything that is higher than the cutoff frequency will be attenuated. So for the derivation of the formula, Fc is equals to 1 over 2 pi Rc. So as we know, the absolute value of Vout is equals to Vin times absolute value of Xc over Xc plus R. Absolute value of Vout over Vin is equals to absolute value of Xc over R squared of R squared plus Xc squared. Then by substituting the Xc by 1 over omega and by manipulating the formula, we will have 1 over square root of 2 is equals to 1 over omega divided by the square root of R squared plus 1 over omega quantity squared. By squaring both sides of the equation, we will have 1 over 2 is equals to 1 over omega squared over R squared plus 1 over omega quantity squared. By manipulating the equation, we will end up with omega is equals to 1 over Rc. When the output changes, the phase also changes. For the low pass filters, the phase change will be equal to negative arctan of omega Rc or Cr. Moving on, the next topic, we will have high pass filter circuits. The high pass filter circuits is the complementary of low pass circuits because it attenuates signals that have frequencies lower than the cutoff frequency and it passes frequencies higher than the cutoff frequency. For the cutoff frequency, we will have the same formula as the low pass filter. We will have 1 over 2 pi Rc. The phase shift P will be equal to the arctan 1 over 2 pi FRC. As you can see in this graph of the amplitude versus frequency, in this the cutoff frequency, it allows signals that have frequencies higher than the cutoff frequency and it attenuates signals lower than the cutoff frequency. This is a RC setup of a high-pass filter. Previously, we had the RC setup of a low-pass filter. And this will be a common graph for the high-pass filters. This is an ideal graph for a high-pass filter. Moving on, band-pass filter. A band-pass filter passes signals within a certain range of frequencies. So how do we achieve that kind of response to the signals? We can achieve that by cascading or connecting the high-pass filter and the low-pass filter. So by cascading or connecting them together, we can produce another type of a passive RC filter that passes a selected range or band of frequencies that can be either narrow or wide, while attenuating all those outside of this range. This new type of passive filter arrangement produces a frequency selective filter, commonly known as a bandpass filter or BPF for short. For the bandwidth, the value of the bandwidth will be equal to the cutoff frequency, higher cutoff frequency minus the lower cutoff frequency. The center frequency will be equal to the square root of FC2 FC2 multiplied by FC1. Moving on, band stop filter, also known as the band reject filter. It is the complete opposite of a band pass filter. It allows signals outside the range of a bandwidth. This is attained by the addition of responses of a low-pass filter and a high-pass filter. If we will divide this graph in half, we can see that this is a response of a low-pass filter in the left side of the graph, and we can see that this response is a response of a high-pass filter. It passes signals with frequencies higher than the cutoff frequency right here, and this attenuates signals with the frequencies higher than the cutoff frequency right here, which is a low pass filter. And this is the phase shift of the band stop filter. This will be the setup for the low pass filter and a high pass filter. So by adding an adder to the low pass filter and high pass filter, we can achieve an output expected to be a band stop filter.